What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 6, Section 1, Exponential Functions. Let's do it. Explain why the values of an increasing exponential function will eventually overtake values of an increasing linear function. So let's look at two different examples. A linear function might be y equals 3x, and an exponential function, just as an example, might be y equals some constant, like 2, let's say, to the x power. So you'll see that what's going to happen as we plug in values of increasing magnitude into x, we get, when we plug in 1, we get 3. When we plug in 2, we get 6, and so on and so forth, right? 3, it's always times 3, so 3, 6, 9, kind of goes up by 3 every time. That's linear. What about exponential? So when we plug in 1, we're just getting 2. So we're starting smaller. But then when we plug in 2 for x, now it's 2 squared, which is 4, still smaller than 6. Then we plug in 3, 2 to the third is 8. Still smaller, but it seems to be increasing. What about 4, right? 2 to the fourth power is 16, whereas over here, we plug in 4 and we only get 12. So this is one example where the exponential will eventually overtake the linear. It just depends where. But this will be the general norm. An exponential will eventually, increasing exponential, of course, will eventually overtake linear. Boom, done. The Oxford Dictionary defines the word nominal as a value that is stated or expressed, but not necessarily corresponding exactly to the real value. Develop a reasonable argument for why the term nominal rate is used to describe the annual percentage rate of an investment account that compounds interest. So the reason why is because when we take compound interest, what's happening is we're taking interest on the interest, if that makes sense. So for example, let's imagine we have a 10% interest and we start with $100. So the first year you put it in the bank and you get 10% of 100, which is $10. So now you have $110. And then the next year, you're not just adding 10 again, because now you've got a bigger principal. Now we're taking 10% of the 111, which is 11. So now we're at 121. So my point is if you were just like, hey, I'm getting 10% of 100 every year, that's incorrect, right? You see that the percentage actually increases as the principal amount increases, right? You're making that $10, now you're adding it in, and now you're taking the 10% on the original 100 plus that $10. So it's 10 plus 1, which is 11. So as you can see, as the years go on, you're not really just getting 10% on $100. You're getting an increased percentage, if you think about it, because you're adding in those extra amounts of interest. So that's why we say the nominal interest rate is actually higher than this proposed 10%, boom, done. For this one, it says a population of bacteria decreases by a consistent factor of 1/8 every 24 hours. That's some sort of a multiplier. So since we know that it's decreasing by a proportional rate every single time, we do have enough information to say that this is indeed an exponential function. So there you go, done. So for this one, it says he charges his clients $5 less than a previous training session. That does not appear to be exponential, and I'll tell you why. So if we start at $100, the next session would be 95. The next session would be 90. The next session would be 85, and so on and so forth. That's a constant rate of change. It's dropping by 5 every time. So there's no rate, there's no proportionate decrease. It's dropping by 5 every time. That's linear, not exponential. So I would say no to exponential, done. So for this one, we're given these two equations for populations of a forest in terms of trees. This one has 1.025 in there. This one has 1.029. So the first question is, which forest population is growing at a faster rate? So that comes down to what's inside this parenthesis, right? And here it's the value above 1. It's 0.025, which as a percentage, if I moved it over, it's growing by 2.5%. So that's for A. And what about for B? It's 1.029 minus 1, which is 0.029, which as a percentage, we move it over twice, is 2.9%. So I would say B is growing at a faster rate. So this question is asking which forest will have a greater number of trees after 20 years and by how many? And since T represents the number of years, right, since start time, we just got to plug and chug 20. So for A, it's 115 times 1.025 to the 20th power. And for B, it's 82 times 1.029 to the 20th power. Now let's plug it into a calculator, Desmos, let's see what we get. So for this one, when we plug in 20 for A, we get 188.4. We'll round to the nearest whole number as 188. And this one will be 145.25, which will round to the nearest whole number at 145. So we have 188 versus 145. So that's a difference of how many? That's a difference of 43 trees. So it will be A by 43 more trees. Boom, done. So for this one, it's asking in the long term, which population is going to eventually win out. And you see that B starts with 82 and A starts with 115. So obviously A starts ahead. But the key is that B is growing at a faster rate, just barely. It's growing at 2.9% versus A at 2.5%, which means that even while A might start off for a number of years as being bigger, eventually B will overtake. So eventually B will be the larger one, and that's going to happen just because, again, the growth rate is bigger. So assuming nothing crazy comes in that disrupts the model, like a drought or a disease or something like that, B is eventually going to be larger. Boom, done. So for this one, we're checking to see if this is exponential or not. This is definitely exponential growth. And the reason why is because we have a variable as the exponent. That's one reason. The other thing, the reason why I'd say this is growth is because the value in that parentheses raised to an exponential power is greater than 1. So our growth factor of 1.6 is greater than 1, so exponential growth, boom, done. So for this one, I'd definitely say exponential. Once again, we're raising to an exponential power, right, for the variable. But is it growth or decay? And what I would say is this is actually decay because this value 0.97 is actually less than 1. By the way, greater than 0 as well, right? Positive, but still in between 0 and 1. And if you want to get technical, this is actually decaying at a rate of 3% per year. So exponential decay, boom, done. So for this one, we're meant to find an exponential equation that represents both of these points. So we've got two coordinates, 0, 2000, and 2, 20. And I know that my format is my initial value times some b value to the x, okay? And we can start with this. We know that when y is 2000, I know that x is 0. And anything to the 0th power, even b or some unknown constant to the 0th power is always going to be 1. So that means a is 2000. So now I know that we've got y equals 2000 times some b value to the x. Now we got to solve for b. Well, I got a second coordinate, so let's plug and chug. 20 equals 2000, and then I've got times some unknown b that I'm still trying to figure out to the second power because x is 2. Now we're going to divide both sides by 2000. 20 over 2000 reduces to 1 over 100, and that equals b squared. Last but not least, take the square root of both sides, and b equals the square root of 1/100th is 1/10. So now I can rewrite this whole equation as y equals 2000 times b, which is 1 over 10, or as a decimal is 0.1 to the x power. And there it is, exponential decay, boom, done. So for this one, once again, we're going to start with that nice formatting of y equals a, b to the x. And we got my first point, which is when y is 6, x is -2. And when y is 1, x is 3. So that means 6 equals a times b to the -2, which is the same as 6 equals a over b squared, because b squared with that -2 goes to the denominator. Now I can multiply both sides by b squared, and I've got 6b squared equals a. I've got enough now to do a little substitution. Check this out. I can plug in 6b squared in for a over here. And I've got 6b squared times b cubed, which is 6b to the 5th, right? We add the exponents. Then I'm going to divide both sides by 6. 1/6 equals b to the 5th. Last but not least, we're going to take the 5th root of both sides. And that means b equals 1/6 and the 5th root of that, which another way to say that is b equals 1 over 6 to the 1/5 power, right? The radical just becomes that denominator of the fractional exponent. Okay, and if I know that this is b, I can figure out what a is by plugging into either of these equations. Let's plug it into this bottom one. So I have 1 equals a times 1 over 6 to the 1/5 power, and this whole thing is cubed. So then now with the exponent rules, I distribute that 3 to that 1/5. So I have 1 equals a times 1 over 6 to the 3/5 power, which means a equals 1 divided by 1 over 6 to the 3/5 power, which is the same as a equaling, since it's in the denominator, it's the same as just saying to the 1/6 to the 3/5 power. Now I have enough, but this is going to look pretty messy. So we have y, or I'll say in function notation, f of x equals, and then first we have that a term, which is 1/6 to the negative 3/5, and then times b, which is 1/6, and that is, again, b is to the 1/5 power, but then I need that x out there. So I can say 1/5 that to the x power, or times x, which is really just simplifies to x over 5. So here is that nice exponential function. It's quite complicated, but that's how you do it. Done. For the following exercises, determine whether the table could represent a function that is linear, exponential, or neither. If it appears to be exponential, find a function that passes through the points. So it looks like as we go up by 1, we're going down by 30 and down by 30 again as we go up by 1 and down by 30 again. So immediately, what am I noticing? I'm noticing that we've got a constant rate of change, aka negative 30 over 1, or negative 30. That's the slope. And when I have a constant rate of change, meaning as every time x goes up by 1, the function value drops by the same amount, in this case 30, that is a linear function. So this is linear. Done. So for this one, as x goes up by 1 every time, right? The function value, it's first going down by 19, then it's going down by, what is that, 18.1, and so on and so forth. So it's kind of dropping like this. So it's definitely not linear. Now the question is it exponential? The way we would tell if it's exponential is if the factor that is multiplying each subsequent time is the same from here to here. So for example, some value times 80 should equal 61. And if it's exponential, that same value times 61 should give us 42.9. So the question is, in this case, what is x? X is divided by 80, we get 61 over 80. And here we divide by 61, we get 42.9 over 61. So the question is, are these two equal? So when we look at these two ratios, we see that they're not the same. This is 0.765, this is 0.703, whatever. So it's not a consistent multiplier. If this was exponential, we'd be multiplying by that same value every time. Let's say if it was 0.75 or something like that, and it would be that same multiplier. So this is a case of neither. Done. So for this one, every time x is going up by 1 each time, and then let's see the change here. It looks like first it's going up by 5.25. Once again here, it looks like it's going up by 5.25, and once again, it's going up by 5.25. That's a constant rate of change. The slope is 5.25 over 1 each and every time, which means if you have a constant rate of change, this is linear. Boom, done. So for number 29, it asks to look at number 28, and it says, what is the initial deposit made to this account up here with this formula where we have A, which is the amount of money in the account total, times something, all this stuff multiplied against each other. And the question is, what is the initial deposit? Well, initial deposit is the principal. It's our P value in this equation. So what is P here? It is that value, $10,250. So that was the initial deposit. Done. An account is opened with an initial deposit of $6,500 and earns 3.6% compounded semi-annually. What will the account be worth in 20 years? So this would be function A of t equals initial, that's principal, 6,500 times 1 plus, then we put that interest rate in decimal form at 0.036, and then it says it's compounded semi-annually. That means twice per year, and that's what goes under here. The amount of times compounded per year, that's 2. To the 2, it's again number of times compounded per year times the number of years, which is t. Now we're trying to find what's the account value in 20 years. So we're finding the value of A when t is 20. So now we just plug and chug in the calculator and see what we get. So once we plug everything in, as we had written down over here, we get $13,268.58. So $13,268.58. Boom. Solve the compound interest formula for principal P, and the formula is A of t, that's just really one constant, we'll say A of t is the principal times 1 plus the rate divided by n, which is the number of times we're compounding per year, to the nt power. And so all we're doing is we're just isolating P. So the first step is I'm going to divide both sides by this. So I get A of t divided by 1 plus r over n to the nt power equals P. And this is pretty much it. Now, if you look in the back of the book, they have almost the same thing, except for they have p equals a of t. And instead of writing this in the denominator, they put this as 1 plus r over n to the negative nt. But this is the same thing, because when you have a negative exponent, it means this would be dropped below 1, right? 1 over that, which is essentially this times a of t is literally the exact same thing. So either of these will work. Boom, done. So for 35, we're looking at the same scenario that we have in 34. So it says, how much would the account in that be worth if it were earning interest for 5 more years? And the key question is how much more? So right now, it's worth $14,472.74. So if we have a of t equals principal times 1 plus r over n to the nt, what we have here is we can kind of plug in and solve for p initially. So we have 14,472.74, that's my a, equals an unknown principal with 1 plus my rate is 5.5%, aka 0.055, that's in decimal format. And it says it's compounded monthly. That's my n value. That's the number of times per year it's compounded, which is 12 to the 12. And then that's my n, and then t is 5. So this is a nice setup to solve for p. So once we kind of solve this out and isolate for p, we see that p equals approximately $11,000. So that's our principal. And now we want to know how much more would the account make if it had it for 5 more years, aka 10 years. So let's plug and chug. So 5 more years would be at 10 years. So a sub 10 equals my principal of 11,000 times 1 plus 0.055 over 12, still being compounded monthly. And then it's 12 times 10 instead of 5. So let's plug this into the calculator and see what we get. So here, when we plug everything in, we get 19,041.84. And the question is, this is how much more than this? So let's run this through Desmos. So once we subtract these two values, we get $4,569.10. So we got $4,569.10 more is what they would make. Boom. So for this one, it says to use the formula found in the previous exercise to calculate the rate for an account that was compounded semi-annually, that's twice per year, with these different values. But what we're going to do is we're just going to use our typical compounded interest formula, and we're going to isolate for r. So let's check it out. So we've got a final value of 13,373.53, and that equals our initial deposit, aka principal, of 9,000 times 1 plus some unknown rate divided by, it said semi-annually, so that's 2 times per year times 2. And then the t value, the time value, is 10. So now we got a nice equation. Now let's solve. So first, we're going to divide both sides by 9,000. So using our calculator, dividing both sides by 9,000, we get 1.48595. I'm going to round it here at that was a 4.7. I'm going to round it to 5, just approximating, equals, and then the 9,000 cancels out. We get 1 plus r over 2 to the 20th power. Now to get rid of that 20th power, or undo this, I'm going to take the 20th root of both sides. Again, I'm going to use my calculator to do that. So taking the 20th root, by the way, is the same thing as raising this to the 1 over 20th power. And this is going to cancel out on this side. And then I have 1 plus r over 2 equals, and we basically get 1.02, right? We get a bunch of zeros, and it's a slight approximation, but it's pretty darn close to this. Then I'm going to subtract 1 from both sides. So we get 0.02 equals r over 2. Multiply both sides by 2. We get r equals 0.04, which means as a percentage, the rate is 4%. Boom, done. So here we have something similar to our continuous growth rate function, which is a equals principal times e to the rt. And whether or not, so it's definitely continuous. It's either decay or growth. But since this value right here, that r value, since 0.75 is positive, it's greater than 0, okay? That means that this is indeed continuous growth. So there's your answer, boom, done. For this one, once again, we have this nice format of a sub t equals principal, which is the 2.25 times e to the rt. And here, my r value is -2. So since -2 is, as we said, negative or less than 0, this is continuous. However, because it's negative, this is continuous decay. So that's how you do it. Boom, done. So for 43, we're meant to look at exercise 42 and compare it to compounded monthly versus compounded continuously. So first, let's set it up for compounded continuously. and that would be a principal of 12,000 e to the 7.2%, that's your r, but you got to put it in as decimal as 0.072, and that's positive, so it's growth. And then it's for 30 years. So let's calculate this in Desmos. So we got 104,053.65. Now let's see what this is compounded monthly. So it's A equals, once again, we have that principal of 12,000, and then we have 1 plus 0.072, that's the rate, and then compounded monthly, that's 12 times per year, and then it's to the 30 times 12, the number of times is compounded per year. So let's calculate this in Desmos. So here we get $103,384.23. And so when we take these two values and you subtract them, you end up with 669.42 or 42 cents. So that is how much less it would be if you compounded it monthly. Boom, done. For this one, we're meant to plug and chug, aka solve for f of -1. So we're going to plug -1 in for x, and we get 2 times -1 plus 3. 2 times -1 is -2 plus 3 is just 1. So it's -4 to the first power, which is just -4. There's your answer. Done. So for 47, we're again plugging in -1. We're taking f of -1. So you plug -1 in, you get -2 times e to the -1 minus 1. -1 minus 1 is -2. So -2 e to the -2. Now anything to a negative exponent is really the same as that value in the denominator to that same exponent, but now positive. So -2 over e squared is correct, but now let's plug it into Desmos and let's get an approximation. So we get -0.2707, so -0.2707 for the approximation. Done. For this one, we're going to plug and chug. We're plugging 3 in for x, so we have 1.2 e to the 2 times 3, which is 6, minus 0.3. So let's evaluate this in Desmos and see the approximation. So we get 483.814, and then we're going to round that 5 up to 6. So we got 483.8146 for the approximation. Boom, done. So for this one, we're going to find the exponential equation with these 2 points. So I'm going to start with our basic format, y equals a b to the x. Next, I'm going to start with this point. When x equals 0, y equals 3. Anything to the 0th power is 1, so that's just 1, and then a equals 3. So now I have y equals 3, and then b to the x, and I'm trying to figure out now what b is. So now I can plug and chug here. We've got 3 for x and 375 for y, so let's write that out. So now let's solve. We're going to divide both sides by 3. That's 125 equals b cubed, and I just so happen to know that 5 cubed is 125, so taking the cube root of both sides, right, like so, we get b equals 5. And if we know that, now we have a nice equation. Y equals a is 3, b is 5 to the x, and there's your exponential equation. Done. So for this one, we're going to start with our basic format of y equals a times b to the x, and I got two different coordinates. So I know that when y is 29.495, I know that x is 20. And I also know that when y is 730.89, I know that x is 150. So now we have two equations. Now we can kind of substitute and solve for these two values. So if I divide both sides by b to the 20th power, I know that a equals 29.495 over b to the 20th power. Now I can take this and I can substitute this in for a in the second equation. So you see I've plugged everything in, and then I have b to the 20th on the bottom, b to the 150th on the top. And the nice thing is it's basically division. So when you have division, you're essentially just subtracting those exponents. So it's 150 minus 120, which is b to the 130th. And then we got that 29.495 in front. So now to solve for b, we're going to divide both sides by 29.495. And then we get b to the 130th equals this, which I'll evaluate in Desmos. So now I get approximately 24.78. And last but not least, we're going to take the 130th root, which is the same as taking this to the 1 over 130th power. So again, taking this in Desmos, I'm just going to go like this, and I'm going to say to the 1 over 130 power, and we get approximately 1.025. So if I know that's b, now I can take this and I can solve for a. So I can plug it into either equation. Let's plug it into this one here. So we're running a little low on room, but we have 29.495 equals a times 1.025 to the 20th. Now to solve for a, I'm going to divide both sides by 1.025 to the 20th. So this is will cancel out. We'll do this in Desmos. And we get 17.99999, but we're going to round that up to 18. So that means a is 18. So now coming back to our original, if we want to write it out, we'd say y equals 18 times b, which is 1.025 to the x power, and done. So for this one, we got some interesting values for the y values. But anyways, we're going to start with that same premise. Y equals a times b to the x. And then we got two different situations. We know that when y is 310.035, that means that x is correspondingly 11, and we also have this coordinate. So then it's this y value equals a times b to the 25th. So now we have some nice values, and now we can isolate and plug and chug. So if I divide both sides by b over 11 for this first one, I'm going to get 310.035 over b to the 11th equals a. Now I can take this and I can plug it into my second equation here. So now we plug that in for a, and then you can see these two simplify. And since it's basically division, 25 minus 11 is 14. So then we're going to divide both sides by 310.035. And then after that, we're going to take the 14th root of both sides, right? That's going to get rid of that 14 over there. So the 14th root of both sides. So let's take this and let's plug it into Desmos. And we now get 1.65 for b. Just one quick thing to note, that in the back of the book, they actually get 1.95, but I believe it's because there's a typo here, or they imagined it here. Because if you make this 356,365 1.9, so basically add one more digit and then a 9 here, then it would have been correct. So I think that the answer was created with that extra 1 and a 9 here. So basically a different number, but I'm going to go ahead and solve it with these numbers. I'm going to show you why at the end that this is actually legitimate. So now that I know b is approximately 1.65, we're going to plug it in to the top equation and solve for a. So now we're going to divide both sides by 1.65 to the 11th and solve for a. And here I didn't really round, I plugged it in as is, as many digits as I can, just to get the best approximation, and then we get 1.22. So a is approximately 1.22, which means now for our final answer, we can say y equals a, which is 1.22, times b, which is 1.65 to the x power. Now, the reason why I said we can verify this is now we got a nice exponential equation. Now, when you plug in 11, we should get this number. When you plug in 25, we should get this number. So let's do that quickly. So here, as you can see, I plugged it in with 11, and I tried not to round because I wanted to give it the most accurate answer. And you'll see we do get that 310.035. Likewise, when we plug in 25, we get 356,365.2 if we round up, and that's what we had as our input before, if you remember, for when x equals 25. So this confirms that this is a reasonable approximation. Boom, done. So for this one, it says repeat the previous exercise to find the formula for APY of an account that compounds daily. So APY from the previous exercise was 1 plus r over 12, but we're going to leave that blank for now, to the 12th power minus 1. But the thing is that the 12 was chosen because it was compounding 12 times per year, aka monthly. So if it's now doing compounded daily, that's 365 times per year, and that's the exponent as well. So this kind of lends to the idea that now if I wanted this to be based on the amount of times we're compounding, literally, if you see what it is, what did I change? I changed the 12 with 365. So now the formula would just be 1 plus my interest rate over the number of times I'm compounding per year. Right here, it's 365 times because it's daily. In 56, it would be 12 because it's monthly. And then to the n power minus 1, there's your function, done. In an exponential decay function, the base of the exponent is a value between 0 and 1. Thus, for some number b is greater than 1, the exponential decay can be written as this. Use this formula along with the fact that b equals e to the n to show that an exponential decay function takes the form of this for some positive number n. So this is a straight substitution problem. If b equals e to the n, I'm going to start by taking this function here and substitute. So the first thing I've done is I've substituted e to the n in for b. Now, the nice thing about e to the n being in the denominator is we can use our exponent rules that when it's in the denominator, I can also rewrite it as e to the negative n. Like that's allowed because e to the negative n is equivalent to this. Then using my exponent rules, I've got this floating exponent on the outside of the parentheses, which means it multiplies in. So now I have f of x equals a times e to the negative nx, right? Those guys multiply. So that's how we know it takes this form. That's how we get there. Done. So for this one, it says the fox population has a growth rate of 9%. That's the rate. In the year 2012, there were this many counted. What is the population to be in 2020? So let's call this times 0. So that can be, my initial value is 23,900. And then we're growing at a rate of 9%. That's 0.09 per year. So that would be divided by 1 if we're thinking about the compounding. But we don't really need 1 because divided by 1 is just itself. And then as to the nt, again, n is 1 because that's the amount of times we're compounding just once per year. So I don't even need to write that here. And then we need to see where is it going to be in 2020. And that's 8 years after 2012, hence an 8 here. So now let's plug and chug in a calculator. And we get roughly 47,622 rounded to the nearest whole number. So 47,622 foxes in 2020. Boom. In the year 1985, a house was valued at $110,000, and then by 2005, it was now worth $145,000. It's gotten more expensive, worth more. What was the annual growth rate between 85 and 2005? Assume the value continued to grow by the same percentage, and then we have to predict in 2010. So we're starting with our initial value of 110,000, and then in 2005, it's 145,000. So that's my ending value. I'm going to put 145,000 equals my initial or principal of 110,000, and it's growing at a certain rate, which I don't know, and it's growing annually, so there's no compounding, so I don't have to worry about divided by n. And this is occurring from 85 to 2005 in 20 years. So now we have a nice setup. Let's solve. First, we're going to divide both sides by 110,000. And using Desmos, we get 1.31818 repeating. Now to get rid of this 20th exponent here, we're going to take the 20th root on both sides. So taking the 20th root is the same as raising it to the 1 over 20th power. So now we get 1.0139, and that equals 1 plus r. Subtract 1 from both sides. R equals 0.0139, which as a percentage, you just move the decimal over twice. It's 1.39%, okay? And then now it says, what was the value of the house in the year 2010? So now we can go back and we can say our value of the house is our initial value, 110,000, times 1 plus 0.0139, 1 plus 0.0139, and then this is to the, instead of the 20th power, now we're talking about 2010, so now that's 25 years from 1985, so 25. So this is the exact value, no rounding, right? This gives you the 1.0139, ... etc. So, and then there we have that plugged into the 25th power, and we get 155,368.09. So the value is $155,368.09. Boom, done. Jalen wants to save $54,000 for a down payment on a home. How much will he need to invest in an account with 8.2% APR compounding daily in order to reach his goal in 5 years? So he's trying to get $54,000. That's the end result. So we need to know how much does he need to start with, aka what's the principal when I've got a rate of 8.2 or 0.082 in decimal format compounding daily, which means we divide by 365. In 5 years. So that's 5, the number of years, times the amount of time it's being compounded per year, which is 365. So now we have a nice equation. Now let's solve for P, and we're going to do it in one step by dividing by this entire quantity. So there we have it written out. Now let's plug and chug in Desmos. And this is the amount that we get when we do all the steps. We get $35,838.76. So $35,838.76 would be the amount that would need to be invested. Boom, done. So for this one, we open a retirement account with this much interest in 2000. Her initial deposit was $13,500. How much will the account be worth in 2025 if interest compounds monthly and then compounded continuously? So let's do these two equations. Now, for monthly, it's the principal times 1 plus that interest rate in decimal format, 0.0725, divided by 12, because it's monthly. That's 12 times per year, to the 12th power. And we're talking 2025. That's so compounded, the number of times compounded per year, 12 times the amount of years, which is 25. And then we're gonna do it continuously, but we're gonna do that in 1 second. But this is the compounded monthly. And for continuously, it's going to be that same initial value, 13,500 times e to the rate, which is 0.0725, and then times the time, which is 25. So let's calculate both of these in Desmos. So for the compounded monthly, we get 82,247.78. Now for the compounded continuously, let's plug and chug. And here we get 82,697.53. And now if we subtract the two of these, we should get, the how much more would you make would be 449.75 cents. So here's the answer to the first part. And here is the difference. There you go. Done. I hope you guys enjoyed this video. And if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.